span of vectors and linearly dependence and independence of vectors, so on. This notion restricted to one vector space, but in this lecture I will tell you given to vector space and how they are related. Tools is linear transformation. Linear transformation be a function given vector space to another vector space which satisfies some nice properties. Definition is let V1 and V2 be two vector space over the field A. Here two vector space but field always be same. Then a function t from V1 to V2 is called linear transformation if it satisfies 1. Tu plus v equal to tu plus tv, where this plus is from V1 and this plus is from V2, or for all uv belongs to V1. That means it is such type if we add two guys u and v from V1, then transform them, and after transformation it is same as first transform them and add them together. Okay. Next property is multiplication with any vector with scalar. Multiply with a scalar with one vector v, this would be alpha v. Then apply transformation, then this would be t of alpha v, which is equal to alpha times tv, where for alpha belongs to field. If we combine these two relation, then this would be t of alpha u plus beta v equal to alpha tu plus beta tv, where for all alpha beta belongs to field and uv belongs to v. And when alpha equal to just 0, then t of 0 equal to always 0. That means every linear mapping takes 0 vector into 0 vector. Now let's see some bunch of example of linear transformations. First example, consider a transformation t from V1 to V2 such that tv equal to 0 transformation. That means here 0 in the vector space V2. So here I have written as V2. This is obviously linear transformation because t of u plus alpha v equal to, by the property of linear transformation, this is equal to tu plus alpha times tv. And tu means here the transformation is given as 0 in the vector space V2. This is also 0. That means this is equal to 0. Therefore, the condition of linear transformation has satisfied here. Our next example, consider identity transformation. Consider I from V to V be linear transformation given by iv equal to v, where for all v belongs to vector space. This is called identity linear transformation. Our next example, consider the vector space R and consider the function t from, here domain and codomain both are, and linear transformation from R to R would be such type. We all of us know one be basis of R and one is basis because any element, any arbitrary element x of the real number can write as x equal to x times 1, where since x be member of real number, so x is scalar and here 1 is a vector. Then t of x equal to t of x times 1, and by the property of scalar multiplication we can write it as x times t of 1. Now consider T of 1 equal to lambda, then T of x equal to lambda times x. Are you getting? That means our defined function is T of x equal to lambda times x. Have you understood how we have considered the defined function? Well, now let's verify. Is this defined function is linear? To prove linearity, consider two vectors x1 and x2 from R. Then T of x1 plus cx2, which is equal to lambda times by the defined function x1 plus cx2. Okay? And by defined function, this is equal to lambda x1 plus c lambda x2. And lambda x1 means by defined function, this is equal to tx1 plus c times tx2. Okay? Therefore, our proof has done our given function be linear. Okay? Now consider V equal to Rn and W equal to R. Similar to before this is, but only extension here. The extension here, the mapping is such type. Consider an arbitrary element x from Rn, and we all of us know standard basis of Rn is look like set containing the element e1, e2 up to en, where ei be the 0, 0, 0 and ith component be 1. After that all term be 0. This is the ith component. Then we can write x as summation I equal to 1 to n xi ei, which is actually equal to x1 times 1 0 0 plus x2 times 0 1 up to all terms 0 up to xn times 0 0, here n term be 1. Then apply the transformation, then tx would be such type t of x1 e1, because this is e1, this is e2 and this part en, and this is equal to x1 e1 plus x2 e2 up to xn en. And by addition formula, this would be t of x1 e1 plus t of x2 e2 up to t of xn en. And here notice one thing, x1 be the here scalar and e1 be the vector. So by scalar multiplication, this is equal to x1 times t e1. Similarly, this is equal to x2 times t e2 up to xn times t en. Now consider alpha equal to t ei, which obviously belongs to real number. Then the mapping is such type t from Rn to R such that t of x equal to summation I equal to 1 to n xi lambda I. Are you getting the mapping? And similar to before, this mapping is obviously linear mapping. Check it on self. That means when the transformation t from Rn to R, then such type of function would be linear. Our next example, consider a transformation t from R2 to R3 given by t of x1 x2 equal to x1 x2 x1 minus x2, where for all x1 x2 belongs to R2. Here notice the mapping from R2 to R3. So here 3 component. Now I will check, is this mapping is linear transformation? To check linear transformation, consider 2 elements from R2. The element look like x1, y1 and x2, y2. Then T of x1, y1 plus c times x2, y2 equal to T of x1 plus cx2, y1 plus cy2, which is by the defined function as like x1 plus cx2, y1 plus cy2, x1 plus c x1 minus y1 minus cy2. And from this line we can write it as easily x1, y1, x1 minus y1 plus c times x2, y2, x2 minus y2. And this is actually similar to T of x1, y1, and this is similar to T of x2, y2. That means the condition of linear transformation has satisfied here. T of x1, y1 plus c times x2, y2 is similar to T of x1, y1 plus c times T of x2, y2. Are you getting? Our next example, T be a mapping from R2 to R2 given by T of x1, x2 equal to x1, 0. This is called projection mapping. Here all vector project on the x-axis. By this definition, our transformed vector would be, this vector would be TV. That means all vector by this expression project on x-axis. I am not going to prove it as before. This is obviously linear transformation. Okay, another example, T be a mapping from R2 to R2 and the mapping is defined as T of x1, x2 equal to x1 minus x2. Where x1, x2 belongs to R2, this is actually the reflection. Consider this vector x1, x2. Here since x1 minus x2, that means reflection about the horizontal axis. Then this vector would be reflex in this vector. Then this would be x1 minus x2. I am not going to verify this transformation. This is obviously linear transformation. This would be satisfy the rule. Next example, rotation. Similar to before, consider the R2. Here the mapping is look like, consider this is x, this is y axis, and consider the vector v. Consider rotation about 45 degree angle. Then after transformation with 45 degree angle, then TV would be such type. Here the transformation vector. And obviously this mapping is linear transformation, because if we scale one vector, then this would be similar to this would be scale. If you add two vector, then rotate them. This is obviously similar as at first rotate this two vector, then add them. So obviously this mapping is example T be a mapping from R2 to R3. The mapping is such type T of x1, x2 equal to x1 plus 2x2, 3x1 plus 4x2, 9x1 plus 10x2. Obviously this is linear transformation. Check it on self. We can write this as T of x1, x2 equal to 1, 2, 3, 4, 9, 10 times the column vector x1, x2. That means in this linear transformation there exists a matrix with this particular linear transformation. And from this idea, we will see one nice theorem. The theorem is every linear transformation related with matrix. Therefore, any real M cross N matrix A gives a linear transformation from Rn to Rm. Here A map from Rn to Rm such that y equal to x, where this x belongs to Rn and y belongs to Rm. Obviously, this is linear transformation. Consider two vectors u and v from Rn. Then add them. Then apply a on u plus v vector. Property of matrix, this part equal to always au plus av. Also, a times lambda u equal to lambda times au. This is also property of matrix. So, any real M cross N matrix A gives a linear transformation from Rn to Rm. Let's verify another example. Consider a mapping T from R2 to R3 such that T of x y equal to 2x plus 3y minus x plus 3y 4x minus 3y. We can write this transformation as matrix from T of xy equal to the matrix whose column vector be 2 minus 1 4 and 3 3 minus 3. Here the component xy. This obviously look like T of xy equal to A times xy. So, by this theorem, we can tell this mapping obviously linear. I hope till now of all my viewers have understood what is the linear transformation. Linear transformation actually a very important concept for any competitive exam and higher study. Which map are linear and which map are not linear? This part is more important for higher study. Now I will see some other different type of linear transformation. T be a mapping from PNR to Pn minus 1R. Here Pn means polynomial of degree n over the field R and Pn minus 1 means polynomial of degree n minus 1 over the field R. Be defined by T of fx equal to f prime x. Here f prime x means the derivative of fx. This is actually called the differential operator. And to prove linear transformation, consider two polynomial fg belongs to Pn R. Then T of alpha f plus g would be by the defined mapping alpha f plus g prime, and by the property of differentiation this would be alpha times f prime plus g prime, and f prime means obviously T of alpha and g prime means T of g. That means this is equal to alpha times T of f plus T of g. Since this relation has satisfied here, so obviously differential operator be a linear transformation. Consider similar type of another function T be a mapping from all continuous function which is defined from closed interval AB to R such that T of f equal to integration a to b fx dx, where for all f belongs to set of all continuous function which is defined on closed AB. Similar to before, this is obviously bilinear map. Next example, T be a mapping from Rm to Rn, where m less than equal to n. Then the transformation is such type T of x1 comma x2 up to xm equal to x1 up to xm. Then other component means minus m components be 0. where x belongs to Rm, then obviously this T is called natural inclusion. Now let's recall this theorem again. Any real m cross n matrix A gives a linear transformation of Rn into Rm, where A be a matrix from Rn to Rm. And this expression always will be true for finite dimensional vector space. When I will create a linear transformation for a finite dimensional vector space, then always I will get one matrix A. And till now, which example I have picked to prove linear transformation, all are finite dimensional. So, for all transformation, I will get one nice matrix. Okay? Now we will see one infinite dimensional linear transformation. Consider R infinity, which is actually set of all sequence x1, x2, so on, where xi belongs to real number. And the mapping is defined as t from R infinity to R infinity, such that t x1, x2 equal to, here 0 component, and x1 shifted to x2, x2 shifted to x3, and this is actually right shift operator. And check it oneself, obviously this operator is linear. This type of example is more important for higher study. What is right shift operator? What is left shift operator? What is differential operator? What is integration operator? This is more important for competitive exam and higher study. Now, consider another type of function f from R2 to R3 such that f of xy equal to e to the power x cos y, e to the power x sin y, comma xy. Consider this component as f1 xy and this component as f2 xy and this component as f3 xy. Now I will check, is this function is linear transformation? There exists a rule. Rule says, when a function defined from Rm to Rn such that f of x equal to f1x up to fnx, when each f1 lies from Rm to R, then this type of function be linear when each fi be linear. And there exists a nice theorem. The theorem is, f who is defined from Rm to Rn is linear if each fi who is defined from Rm to R be linear. That means if each component be linear, then the function who is defined from Rm to Rn be linear. That means for this function, we have to check for each component and check it oneself. Here, each component be linear. So, obviously, our main function means f of xy be linear function. This is one method to check linearity of the function who is defined from Rm to Rn. Consider one easy type of question, but very interesting. Function defined from R2 to R2 such that f of xy equal to x plus 1 comma x plus 2. Is this function be linear? Just think. No. Because here f of 0 0 equal to 1 2, which is not 0 0. So, the function is not be linear map, because for linearity the condition is 0 always map to 0. So, this type of example is not a linear function. Okay? That means for linearity, at first we have to check point 0 0 tends to 0 0. Consider other example, f be a mapping from R2 to R2 such that f of xy equal to x plus y comma 3x minus 2y. Here notice this is f1 component and this is f2 component, and since each f1 and f2 be linear, so obviously this function be linear function. You understood how we have to find linear transformation of a function? Well, I hope my all viewers will can to find linear transformation of functions easily. In my next video, I will discuss this topic also elaborately. But I will highly recommend you, please see today's video with pay attention. And if you have any queries about today's video, please do comments in comments box. See you soon. Stay safe and stay positive always. And don't forget to do subscribe my channel. Thank you so much.